no scientist that you talk to now would say that the big changes in the Arctic are not having impact on weather patterns. It's just really a question of unraveling exactly how, because it's not the same every year, it's not the same everywhere. And so really kind of getting down into the weeds of how these mechanisms basically work.
Welcome, everyone, to Biodiversity for a Livable Climate's monthly speaker series, Life Saves the Planet. This month, as you all know, we are honored to have Jennifer Francis speaking about Arctic meltdown, why it matters to us. Adam Sachs, Biodiversity for a Livable Climate's Executive Director, is going to be the moderator for the event. But first, our speakers. Dr. Francis spent several years, 5 years, in the early 1980s with her husband sailing around the world, and her interest in Arctic weather and climate was sparked by a summer spent sailing near Svalbard. She went to school from 1994 through 2018. She was a research professor at Rutgers University. And in 2018, she joined the staff of Woodwell Research Center in Falmouth, Massachusetts as a senior scientist. She is still there as senior scientist, but also as deputy director. Her research has focused on climate change in the Arctic. She's published over 40 scientific papers, spoken to many groups, including the Congress of the United States. And basically what she is telling us is that melting ice in the Arctic is changing or may be changing the jet stream, which is leading to abnormal weather patterns. She has also pioneered throughout her career the use of satellite data to understand the dramatic changes taking place in the Arctic and how the disproportionate warming there is affecting temperate regions on Earth. I want to say that Dr. Francis is committed to making scientific information accessible to ordinary people, to the public, and that is one of her missions. It is also a mission of the person who will be joining her after her presentation. Heather Goldstone will talk with Dr. Francis about the ramifications of the work that she presents. Dr. Goldstone has a degree in molecular biology and oversees Woodwell's climate communications and communication activities. She has extensive experience both as a scientist and a journalist, and is very interested, not only that, but passionate about putting together data and narratives in climate change stories that build awareness and inspire action. She came to Woodwell from GBH, where she founded and hosted a weekly science-focused radio show, Living Lab Radio. Previously wrote a Climatide blog about coastal communities facing climate change, and she has appeared in many outlets, including NPR's Morning Edition, The Takeaway, and PBS NewsHours. Thank you very much for being here with us.
Thank you very much, Paula, and thank you for having me on the program tonight. It's an honor to be here. I just want to point out one little thing, and that is Paula mentioned that I joined the Woodwell Research Center, and we are now the Woodwell Climate Research Center. So that's why there's a little difference in the naming there. So I'm going to go ahead and share my screen at this point. Good evening, everyone. Tonight, as Paula mentioned, I'm going to be talking about why we should all care about what the big changes that are happening up in the Arctic. Well, you probably know it's warming very quickly up there. It's also melting very quickly. And this picture gives you a little hint about one of the reasons why what's going on up there matters to all of us, especially as we see another very strong nor'easter approaching New England for this weekend. As we see sea levels rising, which is what is being shown in this photograph, we know that when a storm does come ashore now, it tends to have a bigger impact in terms of coastal flooding and wave damage because it's riding on top of a higher sea. And the Arctic has a role to play in this, which I'll talk about soon. But first, I want to talk about some extreme weather, because that's another way that the Arctic is affecting us. And if we look back at just a couple of events that happened just this past year in 2021, you'll probably remember that the Pacific Northwest endured one of, well, the worst heat wave they've ever experienced as far back as we have records. And what this map is showing you here are temperature differences from normal. And the red colors are where it's much warmer than normal, and the blues and greens are where it's colder than normal. So back in June of 2021, this is what it looked like during that heat wave. This big blob of red colors here is showing us just that extensive area of extremely warm temperatures. And that made headlines, and it was really tough for the people living up there. But what I also want you to notice, and you don't hear about this in the news, is that right next to this big heat wave, there's a cold wave, if you could call it that, happening down in the southwestern states. And then again, we see warm temperatures over in the northeastern states. So what I want you to notice then is that when we have an extreme of one flavor in one area, you almost always have unusual weather of a different flavor right next door. And we'll talk about that some more. What caused that big heat wave? Well, whenever you think about extreme weather events across the United States or across Eurasia, your mind should automatically think about the jet stream, because the jet stream creates and steers pretty much all the weather that we experience in what we call the mid-latitudes, which is the region between the tropic and the polar regions. So on this graphic here, you can see these blue words here outlining the path of the jet stream. And during this event, you can see that the jet stream took this very unusual, convoluted northward swing way up into the Pacific Northwest. Now, the jet stream separates the very warm air to the south from the much colder air to the north. So when we get one of these big northward swings, it allows all that warm air to extend much farther north than it normally would. And this is indeed what caused that heat wave. But also, when the jet stream is in one of these very convoluted paths, it tends to stay there for a while. These big waves tend to kind of get stuck in place. And that means that the weather associated with them also tends to last a long time. Now, remember, though, there was that cool, unusually cool area down in the southwestern part of the country, and you can see why. The jet stream was bringing all of this cold air down from far northern Canada all the way down to Arizona. And that's why it was unusually cold in that area. So again, the jet stream is the reason that happened. So there was another very disruptive extreme event that happened a little earlier. In fact, we're coming up on the anniversary of this very severe cold wave that struck a good part of the middle of North America. And on this day, back in February, we saw temperatures in Dallas that were colder than temperatures in many places in Alaska and Greenland. This was a very unusual event for several reasons, not only for the extreme cold, but also the great area that it covered. It lasted a very long time, and it went all the way down to the border with Mexico. So this was a very extensive situation here. And what was going on? Well, you remember what I just told you, think jet stream, all right? So now we've got these words here that say storm track, jet stream, kind of the same thing. So instead of having that big northward bulge that we saw with the heat wave, instead we have this huge southward dip. And that allowed all the cold air that was bottled up in the Arctic to plunge way far south. Now, on top of this, you see this other thing here called the polar vortex. And I know you've heard of that now. It's a common term that the media tend to use. And I have to say that oftentimes it's not used correctly. So tonight, you're going to learn what the polar vortex really is so that you can talk about it properly. So if we look down now on the North Atlantic. So here's the United States over here and Europe on the other side. We have these two circular blue rings around the North Pole. The light blue ring here is the jet stream that we've been talking about. It's actually never this circular, it always has some waves in it, but just for this diagram, we'll call that the jet stream. It sits about 5 to 9 miles above the surface, up where jets fly, hence its name. And then much higher in the atmosphere, more like 10 to 30 miles above the surface, there's another swirling pool of very cold air. This is the polar vortex. More correctly, it would be the stratospheric polar vortex. It's only there in the wintertime, whereas the jet stream is there all the time. So the polar vortex sits over the North Pole. It spins around with strong winds encircling this very, very cold air. And most of the time, it has very little impact on our weather. It just sits up there and minds its own business. But every once in a while, that stratospheric polar vortex gets disrupted. And by disrupted, I mean it can stretch into kind of a bean shape instead of being circular. It kind of gets stretched out, or it can even split into two parts. And back in February of last year, this is exactly what happened. We had a very strong disruption of the polar vortex, and that allowed one of these pools of that extremely cold air to dip southward over North America, while another patch of that cold air went down over Siberia. And this helped reinforce and intensify that very cold air that came down over the middle of the country. It also made the jet stream take an even bigger dip southward. And again, what you see right next door here is this pair of extreme events, and you'll see how this turns up in the temperatures in a second. But whenever you get a big, strong dip in the jet stream, you almost always get a rebound downstream. And if we step back and look at what the temperatures look like around the northern hemisphere at that time, we look over North America here, you can see these blue colors are telling us it's much colder than normal. And right next door, where that jet stream was rebounding from the southern dip and going northward, we can see all these very warm temperatures because of all that warm air that was being brought northward. Now, if we jump over to Eurasia, we can see also that the temperatures were very cold in a big part of northern Asia. But again, we see this other type of extreme conditions happening right next door with much warmer than normal conditions happening over a big section of China. So these kinds of extreme events seem to be happening more often, and in fact, they are. And it's not just us scientists who are keeping track of this. There are companies like insurance companies who really care about extreme events because they end up paying the tab when there's a lot of damage. So this graph is from a company named Munich Re. It's one of the biggest reinsurance companies in the world. And what they keep track of is the frequency of billion-dollar damage extreme events. These different colored bars here that go back to 1980 up to almost present are for different kinds of extreme events. All of them are related to weather or climate, except for these red ones, which are things like tsunamis and volcanoes and earthquakes. And you'll notice that they are not changing over time, but the weather-related ones, in fact, have tripled just since 1980. And if we look at the most expensive extreme events, this is a chart prepared by Jeff Masters recently, looking at the $20 billion plus extreme events, we can also see that those have increased over time. So these are the mega disasters. And this year was a very damaging year. So let's go back to temperatures again now. And you've all heard of global warming, of course. And you're used to looking at maps of how temperatures have changed over the Earth over time. But this map shows you something a little different. This shows you how temperatures have changed relative to the global temperature change overall. So what this means is that places that are blue have warmed less than the globe has as a whole, and the places that are red colors have warmed faster than the globe as a whole. So what jumps out at you right away is that the oceans have generally warmed slower than the global average, while the land areas are warming faster. But what really jumps out is these bright red colors up in the far north. And this is telling us that the Arctic is warming much faster than anywhere else. Right now, it's warming about 4 times faster than the globe. And associated with those warm temperatures are the loss of various types of ice and snow in the Arctic. Here I'm showing you how the thickness of the sea ice, which is the ice that floats on the Arctic Ocean, has been changing just since the late 1970s, so over the last 4 decades or so. And so here's Greenland, there's Europe on this side, here's Alaska down in the bottom left, and these colors all represent the thickness of that ice floating on the Arctic Ocean. And what you can see very clearly in this beautiful animation by Zach Labe is that these yellow and white colors, which represent the thickest ice types, are almost completely gone when you look at the latest years here. They're basically not there anymore. So this is telling us that the ice is now much, much thinner. And when ice gets thin, it's much more vulnerable to any weather anomalies, changes in temperature, or changes in winds. And so it's a much more fragile ice cover. So that was the ice thickness. We can also look at what's happening to the ice cover. So up here in the upper right, the white area here over the Arctic Ocean is showing you what the ice cover typically looked like in September, which is when the ice melts back to its smallest state in the year. And so back then it covered most of the Arctic Ocean. And then if we jump forward here to 2012, which was the year when the ice reached its lowest, the lowest record ice cover that we've seen so far. It's about half as big as it was only back in 1979. And these yellow and red colors here are showing you where the ice used to be. So instead of having all of this white ice covering the Arctic Ocean, we now have much more open water. And that open water is dark. And it absorbs a lot more of the sun's energy. It warms up the Arctic Ocean, and that melts even more ice. So it sets up a vicious cycle in the climate system, which is the main reason why the Arctic is warming so much faster than anywhere else. So as I mentioned, this change has happened very rapidly, only in about a 40-year time period. And if we take into account the change in the coverage and multiply it by the change in the thickness that I just showed you, we get a change in volume that is about 75%. That's the loss. So this is a huge change in a very, very important part of the climate system. So literally the Arctic is darker now. That means the Earth is darker. It's absorbing a lot more of the sun's energy just because of the loss of ice and snow. And this factor alone is leading to global warming being about 25 to 40% larger than it would be otherwise. So this is a big impact just on the underlying problem that is driving so many other changes in the climate system. And as the Arctic warms rapidly, it's also causing the Greenland ice sheet to melt much faster. When that ice melts that's sitting on land, it adds mass to the ocean. And so it is now the biggest contributor to sea level rise. So going back to my very first slide, the rapid warming in the Arctic is causing the acceleration of sea level rise that we're observing now. There's also a lot of ice trapped in the soils in high Arctic areas. This is called permafrost. And we know that permafrost is warming and it's starting to thaw. And this is a very big deal because that permafrost, that frozen soil, contains a lot of organic material. And when it starts to thaw, the microbes in the soil can start to break it down. And when they do that, they release either carbon dioxide or methane into the atmosphere. Both of those gases, of course, are greenhouse gases. So they add to the problem. This is another vicious cycle that goes back to the changes in the Arctic. And finally, as I alluded to a little bit, and Paula mentioned in the beginning, we think that the rapid warming in the Arctic is also affecting the winds of the jet stream. And as you now know, anything that messes with the jet stream is going to mess with our weather. So that's what we're going to talk about now. Now, to understand how this is happening, I want you to think about a layer of air that extends from somewhere in the United States, wherever you are, up to the Arctic. And we know that when air is warm, it takes up more room, or air expands as it warms. And so this layer is going to be thicker in warmer places down here over the United States or mid-latitudes than it is up in the Arctic. So this layer is going to form a hill in the atmosphere. If you were sitting on top of this layer and looking northward, you would be looking down a hill. Well, the air sitting on top of that layer wants to flow down that hill, just like water wants to flow down the side of a mountain, and that creates a wind. But because the Earth is spinning, that wind gets turned to the right, just like anything that moves in the Northern Hemisphere. And so this creates a west to east flow of wind that we call the jet stream. So now think back to what's happening in the Arctic and the fact that it's warming so much faster than anywhere else. This is causing the layer to expand more in the Arctic than it is in mid-latitudes. So the effect is to make that hill less steep. So there's less force driving that wind of the jet stream. And as a result, we see that the west winds of the jet stream are weakening. And we know that when the jet stream is weaker, it tends to be wavier. It tends to take these bigger north and south swings, like the ones I showed you that created those extreme events. It's more easily deflected by things like mountain ranges or even by blobs of water out in the ocean that have unusual temperature patterns. So that's basically why the jet stream is there. And why are we making such a big deal about these waves in the jet stream? Well, I already showed you those extreme events and how they're tied to the jet stream. But these waves really are key to all of the weather that we experience here in the United States and over in Eurasia as well. So I mentioned that the jet stream, which is indicated by this purple arrow here, separates the warm air to the south in the tropics from the much colder air to the north. So if the jet stream is south of you, then you're going to be on the cold side and vice versa. But these waves also create upward and downward motions in the atmosphere that create, on a weather map that you'd see on TV, the highs and the lows. The highs tend to be clear blue skies and dry conditions and nice weather, and the lows tend to be associated with storms. Well, this part of the jet stream right here, where the winds are coming out of the northwest, is where you find the high pressure areas. It's where it tends to be dry and sunny and clear. And this part of the jet stream is where we tend to find our storms. So as you can imagine, we're going to have this sort of a situation coming up this weekend in New England because we are looking towards that nor'easter coming up the coast. This is the situation. This is what the jet stream is looking like basically when we get our big storms along the coast of New England. So the jet stream really does create all of our weather. But sadly, it's not as simple as that. Here is what a real jet stream looks like. This is about 3 weeks of actual wind data plotted by NASA. You can see these red and yellow colors are showing you where the winds are very strong. And over North America here, you can see a very typical jet stream that is just an absolute mess with all kinds of swirls and waves. And you can imagine it's very difficult to measure whether in fact the jet stream is changing over time. And I can tell you that's not easy. But the other thing I want you to notice is that sometimes these waves are small and they progress really quickly across the continent. And then sometimes they get really big and they get stuck in place for a long time. So that goes back to what I said about those really convoluted jet stream shapes that created those extreme events that I mentioned in the beginning. But just keep in mind just what a chaotic situation this is and how difficult it might be to try to measure changes in the jet stream over time. So that's the jet stream story pretty much. And I want to sort of wrap up by going back to the sea ice. And so what I'm showing you here now is a plot that shows you how sea ice has changed in the past in terms of its coverage at the end of summer. You remember I showed you those two maps that showed how much area was covered by sea ice in September. Well, this is plotting that area coverage, that total area over time, going back to the beginning of the 1900s and all the way out into the future. So there's a couple different lines on here. First of all, this dark black line is what actually happened on Earth. So these are measurements from satellites mainly, and you can see this very dramatic decline that really got started kind of in the mid 1990s or so, right up to present day. These other fuzzier colors on here are showing you simulations by these very complicated computer programs that we use to simulate what the climate system is doing. So basically, they take all that we know about the processes in the climate and we put that into mathematical equations, and we can run these models to help us study the past, but also help project the future. So going back in time here, you can see that the climate models have a lot of wiggles in each of their simulations, just like the real world does. And that's why there's this cloud around an average line here. Those are wiggles that happen in the model, just like in the real world. But you can see the model does a darn good job of capturing the changes that happened in the real world. But as we go forward in time, of course, we don't know exactly what's going to happen. And there are different possibilities of what could happen. And those possibilities all depend on us. So this red line here is what I call the do nothing line. Is this, if we just keep going as we're going, using fossil fuels, using plastics and materials, basically not changing our behavior, then we're looking at a future in the not too distant future where we're going to see an Arctic Ocean with no ice in it in the summertime. That's probably going to happen sometime around 2040 or 2050 for the first time. This is a pretty widely believed event that we think is going to happen. However, if we're able to get our act together and really cut down our emissions of greenhouse gases, especially the carbon-based ones, and look to natural solutions to try to help the Earth absorb more of that carbon from the atmosphere, we can aspire to follow this green line here. This green line is keeping quite a bit of ice in the Arctic Ocean, even in the summertime. And if we can do that, it'll mean we won't see the accelerating sea levels as fast as could happen if we stayed on the red line. We'll see not quite as bad extreme weather in the future, and all of the other impacts of climate change just won't be quite as bad if we can manage to stay on that green line. So how are we going to do that? Well, it really comes down to two very simple things, and I've already alluded to them. So the first is just to emit less heat-trapping gases. These are the greenhouse gases, carbon dioxide, methane, nitrous oxide. Those are the main ones. The other, again, is to create more gas absorbers, or to help the absorbers that already exist naturally in the climate system to do their job. So let's take a little closer look at what this means. So we can simplify these two things in a graphic here and help think about how this works. So if we think of this bathtub of water here as indicating how much of these greenhouse gases are in the atmosphere. So the water is the concentration of those greenhouse gases that are trapping all the heat and causing all these problems. Well, the bathtub has a drain, which lets water out, and it has a faucet that puts water in. So the faucet is these greenhouse gases that we're dumping into the atmosphere, mainly by burning fossil fuels. And right now, the water coming in from the faucet is much, much larger than can go out the drain. The drain is all of the things that absorb these greenhouse gases from the atmosphere. So the algae in the ocean, our forests, the microbes in the soils, there's all kinds of things that naturally occur in the climate system that remove carbon. So if we think about then how we can do some of these things, we know that these heat trapping gases are coming from burning fossil fuels, from driving cars. And if we look at exactly how they're distributed, we see that these greenhouse gases are mainly coming from these burning fossil fuels through industrial processes. Methane is another fossil fuel. We call it natural gas. I don't call it natural gas anymore because I think that's making it sound like it's something that's okay. It's not okay. Natural gas is methane. It's a fossil fuel. Some carbon dioxide comes from forestry, where trees are being cut down, filling in of wetlands, things like that. And then nitrous oxide is another greenhouse gas. So a lot of the human activities that are causing these fossil fuels to be burned involve the generation of electricity and heat in our homes, agriculture, transportation, of course, industry. So you can kind of get a sense for where some of these gases are being generated. So now if we take a look at where the gas absorbers might be, where we might help them do their job. Of course, I mentioned forests, especially tropical forests, which right now are being deforested. We've got to stop doing that. We've got to start encouraging those forests to be healthier, plant more trees. We can help by feeding animals different kinds of plants, especially legumes, for example, which not only cause the animals that eat them to produce less methane naturally in their systems, but it also helps put nitrogen and other minerals back into the soil. So it makes the soils healthier. A lot of these natural solutions have more benefits than just the reduction of carbon in the atmosphere. We need to stop destroying mangrove swamps. They've been destroyed in many areas of the tropics, and they are huge in terms of drawing carbon out of the atmosphere, as are all kinds of other wetlands, whether they're salt or freshwater. So these are all the natural solutions that we really need to focus on, helping them become better at what they do. And on a more individual basis, there's a lot of choices we can make in our lives every day, the kinds of transportation we use, whether we fly less often, whether we purchase a car that gets more miles per gallon, helping our homes be more efficient in terms of how much energy they use, buying appliances that are more efficient, and basically trying to conserve as much electricity and other types of energy as possible. And not only are you saving that energy, but you're also saving a lot more energy because it takes a lot of energy to, for example, get an electron to the plug in the wall in your home. So we can all get more involved, perhaps, in our community governments. This is big in terms of helping to prepare for the future with more of these extreme events that I've been talking about. We need to identify where our communities are vulnerable, whether it's infrastructure or personal property, and we can help our towns start to plan proactively once we accept the fact that this is a future that is coming for the next couple decades. No matter what we do, we're going to be seeing stronger storms. We're going to be seeing more extreme events. And so we do need to get ready for those, whatever they are in your particular area. We can support our towns transitioning away from fossil fuels, and our neighbors, help them understand how important this is. We can join committees, and we can even run for office in our towns. It's amazing how much one person can accomplish, especially in a small New England town. And then, of course, at the state and national level, one of the most important things we all need to do is vote for leaders who understand what an incredible crisis the climate crisis really is, and that the solutions to it are not going to be easy, but those have to be made. I think a real simple thing that needs to be done is to stop subsidizing the fossil fuel industry. Every year, we're subsidizing them by about $600 billion. That's with a B. And all that money could instead be used to go into promoting more renewable energy sources and improving the grid to accept those renewable energy sources. And of course, we need to more appropriately price the carbon that we do emit. So finally, you're here listening, which is great. You're educating yourself. And now you need to go and talk to your neighbors and friends. And just as a final couple of messages, what we're all trying to do now is avoid the unmanageable and manage the avoidable. That's kind of where we are right now. We also know that the impacts of climate change are affecting the people who are least able to be resilient to their impacts. And so we all need to keep in mind that there are people who had very little to do with this problem who are really suffering the worst impacts. So with that, we can hand it over to Heather.
I always have, I have a whole page here of questions that I've jotted down, but I have a couple I really wanted to ask you. And one is, what about the Southern Hemisphere? I mean, especially with what you were just saying in terms of the world's most vulnerable are suffering the worst impacts. Maybe it's just a bubble that I live in. I don't hear as much about Southern Hemisphere extreme events. Certainly there were the fires in Australia a couple of years ago. Is the same thing happening in the Southern Hemisphere?
So the Southern Hemisphere has a very different weather system. It has a lot of very big differences that affect how climate change is basically manifesting itself. I should say, though, just in the last couple of weeks, they've had some really horrific heat waves, both in South America and in Africa. And they've set some new records for many countries in those regions. So they're having their summer now, of course. And so they are experiencing some very severe heat waves and fires, especially. So there are a lot of differences, as I mentioned. First of all, they don't have their South Pole area warming rapidly like the Arctic is. And the reason is because the Antarctic is a continent and it's covered in a big, thick sheet of ice, like a couple of miles thick in most places. And it does grow sea ice in the winter, but that sea ice melts back all the way to the coast every summer. And so there isn't this opportunity for the ice to melt more and then expose more dark ocean, which warms the water, which melts more ice. There isn't that vicious cycle happening down there. So they're not seeing the same acceleration of the warming or amplification of the warming that we have in the Arctic. And so we're not seeing this effect on the jet stream quite the same way. But the ozone hole down there is having an impact. And the impact there is actually to strengthen the winds of the jet stream and make it contract farther south. And this is why they're having worse heat waves, or one of the reasons why they're having worse heat waves is because this time of year now, the storms are not making it as far north because that jet stream has contracted farther south. And so they're not getting the frontal passages that they would normally get to bring in some cool air or some rain. And so it's a very different story down there, but they are, of course, being affected. And we are also noticing now that the glaciers that come off of the Antarctic ice sheet are melting from below because of the warming ocean water. So the ocean warming is the other big component of sea level rise. And as the undersides of those glaciers melt, they are adding more mass to the ocean too. And this has a huge potential to accelerate sea level rise.
Jen, you've told me, and I think said publicly many times, that your commitment to climate change communication was in large part sparked by how controversial some of your research was and the very mixed attention that it got back in 2012 when you started to put out this idea that disproportionate Arctic warming was affecting our weather through the jet stream. Why was it so controversial? I mean, when you walk it through us tonight, it seems very logical. You have examples, you have, why has it been so controversial and where does the science stand?
Mm-hmm. That is an excellent question. It is still controversial, though I would say that no scientist that you talk to now would say that the big changes in the Arctic are not having impact on weather patterns. It's just really a question of unraveling exactly how, because it's not the same every year, it's not the same everywhere. And so really kind of getting down into the weeds of how these mechanisms basically work. But yeah, so back then it was very controversial because pretty much when it came to unusual behavior in the jet stream, most atmospheric scientists looked to the tropics. They looked to El Niños and La Niñas. They looked to temperature patterns in the Pacific Ocean and how those were changing. And the tropics are much, much bigger than the Arctic. And this has been kind of an area of research that's been going on for decades and decades. And so there was a lot of sort of baked in knowledge and accepted theories of how the jet stream was being affected by things. So it was kind of rocking the boat for a lot of atmospheric dynamicists, especially to have this other idea come along, and especially referring to this little top of the earth that seems so far away and insignificant to have this impact. But a lot of people thought it made a lot of sense, and it's taking a while, as I said, to really figure out all the mechanisms and how it actually happens. But as I said, I don't think anybody now thinks that it's not a thing.
Yeah, it would be hard to when you watch what's going on with our weather, for sure. But I think just thinking about, well, maybe like you said, when the tropics is this big area and the globe, generally speaking, obviously it's always changing and weather is changing, but this system is kind of stable. Maybe the tropics has more of an impact, but when it starts to change, I mean, it's got to also be really difficult to get a handle on what's happening. These are changes that we've never seen in the history of any of our record keeping. It's changing incredibly quickly to even, and you alluded to this a little bit, like the jet stream is chaotic, and we're seeing processes that we essentially have never seen before, right?
Yeah, I don't know if I would say that the processes have never been seen before, but if you're thinking about those extreme waves in the jet stream that we know are associated with extreme events, those happen naturally. But what we're seeing is those wavy conditions happening more often. So it's not something like, the jet stream's doing things that we've never seen before. It's just that it's acting in an unusual way much more commonly now. And so that's really how to think about it, I would say.
Adam, I know we want to get to audience questions. Do I have time for one more, or do we want to jump over to some other folks' questions? I'm happy to share.
Is this a quick question?
Jen, every time I hear you give a version of this talk, it sparks new ideas. And I was watching you talking about, the flattening of the hill because of the disproportionate warming and how that slows down the jet stream, makes it different. I mean, could we ever get to a point where the warming has gotten so extreme and so disproportionate that the jet stream essentially stops, just kind of falls apart?
No, because
there we go. We'll keep it at a short question. No,
that was such a short answer. No, it's a quick answer, actually. And that's because it's always going to be colder at the North Pole and in the Arctic than it is farther south, because that depends on the sun, and the energy that the sun puts gives the Earth is much stronger in the tropics than it is in the pole. So we're going to have ice forming in the winter, probably for at least another couple of centuries on the Arctic Ocean, that is. And so it's always going to be colder there, and that temperature difference is always going to create a jet stream. So, yeah.
There's a little bit of reassurance there. Yeah. All right, over to audience questions.
Well, you're not going to live to see it, put it that way. That is a form of reassurance. So we have a question from Patricia, who says, how hopeful are you, Jen, that it's still possible to reverse this?
So if you remember back to that green line that I showed you, it does not go back to where we used to be. We pretty much cannot reverse it. What the best we can hope for is to make it as less bad in the future as we can. So we can lessen the impacts in the future, but we cannot turn it around. I'm sorry. But I am hopeful. I'm very optimistic that we can put us on that green line, and that green line will give our kids and our grandkids a future that looks a lot more like the one we have than what it could be if we stay on the red line.
Okay. how much potential does regenerative organic farming and landscaping have to help reduce these problems?
Well, the agricultural sector right now is a big source of greenhouse gases. And we have folks at Woodwell who are experts in this field and are studying many different ways where we can help the agricultural sector still farm, but to do it in a much more in a much better way to keep the soils healthy and to not release as much carbon dioxide into the atmosphere, perhaps even turn those soils into absorbers. So I think there's a huge potential to make a big dent in that piece of the pie by changing the way we farm, basically, not just grow crops, but also what we feed animals. And of course, we could all eat less animals because those are definitely produce more carbon per calorie than, say, a plant-based diet. But if we all just ate a little less meat, that would also have a big impact.
Adam, can I just join in on that for 1 second?
Sure.
I mean, everything that Jen said, absolutely changing the way we use the land that's already allocated to agriculture is super important. But the other thing is to realize that agriculture globally is one of the main drivers of deforestation. And one of our colleagues said this to me earlier this week in a way that I had not heard it before, and it was really powerful. The world's tropical forests are essentially holding back an extra degree of warming, that if we didn't have them, we'd already be another degree warmer. And so keeping those forests in place and making sure that we're not deforesting to expand agricultural land is really one of the most important things we can think about in terms of how we farm and how we produce food. And obviously that balance, right, of keeping the forests and also providing food and providing livelihoods for people who live there, balancing those two is, it's a huge challenge, but it's also a really exciting area of research and work right now.
Okay, audience question. Why is New England warming faster than the rest of the world?
Well, New England is not warming faster than the rest of the world. It's definitely warming faster than some places, partly because it's so far north, and it's feeling those effects of those vicious cycles that happen where there's snow and ice around. The other part of that story is that we have the Gulf Stream off of our coast. The Gulf Stream brings warm water from the Gulf of Mexico all up the eastern seaboard before it heads across the North Atlantic. And in the last few decades, there's been some very recent research that suggests that those large-scale Atlantic currents may actually be slowing down somewhat. And that has the effect of kind of backing up that warm water along our coast and resulting in the warm waters that we've been seeing there for the last 5 or 6 years. The temperatures have been running way above normal. We know that's true, especially along the South Coast, where the lobster fishery is basically gone. But up in Maine, the waters have warmed quite a bit and actually made it more favorable for lobsters. And so lobsters are booming up there. And that's partly because of this overall warming that's been happening in the region. But yeah, New England's warming fast, but certainly not the fastest of anywhere.
Yeah, I'm wondering if they're referring to the ocean temperature warming. And it's interesting, we tend to talk about when a place is warming, we're referring to the atmosphere, right? Not to the ocean. The waters off, as you just explained, the waters off our coast are warming faster than almost anywhere else in the ocean, but the air temperatures aren't necessarily. So different parts of the system doing different things.
But the ocean has also absorbed 90+% of the heat that hasn't gone into the atmosphere. How do we deal with that?
Well, it's the same solution that we have to deal with the whole underlying disease. So, the oceans aren't warming as fast as the globe, as I showed on that one map there that had the oceans all basically blue. And that's because it takes a lot of energy to warm water, much more than it does to warm air. And so there is a lot of heat building up in the ocean, and it's going to take a long time for that heat to leave the ocean too. So, but the solution is the same. It's emitting less carbon into the atmosphere and absorbing more of it into natural solutions. And if we can come up with technological solutions too, then great. But the solution is the same.
I have a question here, which is pretty interesting, I think. Could you say a bit more, other than the jet stream, about the consequences of the temperature differential between the Arctic and points south?
It's certainly causing those far northern regions to change much faster. We're seeing the soils dry out much earlier in the spring in sort of higher latitude areas where the snow would generally last till April or May. It's now leaving 3 or 4 weeks earlier. And once that happens, the soil underneath can dry out sooner. And once the soil gets dry, it can warm up really fast. And this is one of the factors that's driving the intensity of heat waves becoming, much more intense over the last decade or two across the continents. That disappearance of the snow and the rapid drying of the soils. And this basically gives summer a jump start because it's warming those soils and it's heating the air and making fire weather more likely. And so it's also playing into the increased wildfires that we've been seeing too. So that's one example.
Okay. And one more question that I'm sure you've wrestled with a lot. Isn't it hard to get the public to understand when a timeline is beyond their lifetimes?
Well, I think most of us have kids or grandkids, and we want to leave them a situation, a life that's good and healthy, and it's an earth that has the beautiful places that some of us have enjoyed as we've grown up. So I think if people can think about their offspring rather than just themselves, then they might have a very different outlook on needing to address this crisis.
Doesn't it imply that we have to make some very serious lifestyle changes and expectation changes?
Well, energy is one of the biggest sectors that we have already, the tools, the technology, the wherewithal to shift away from fossil fuels. That all by itself would be a game changer in terms of getting us onto that green line. We can do this. It's in our grasp already. So, and that does not require big lifestyle changes because we're just generating electricity a different way. We can also create fuels for transportation using different methods that don't require fossil fuels. So there's a lot of new technology being developed. I hear about new things every day practically. That gives me a lot of hope that we can transition to this future that doesn't require us giving up the things that we love to do. We love to travel, we can still do all those things, but we just have to be a little more mindful of not wasting energy, not wasting materials, not wasting food. We waste a lot. And so that's another place that we can make a big difference without really changing our lifestyle.
Okay, we have a bit less than 2 minutes left. So Heather, do you want to give some closing comments? And Jennifer, will let you wrap it up.
Yeah, I'll just kind of piggyback on what Jen was saying and drive home the point that while there are still many scientific questions and things to learn, there are more technologies that we can develop. There are more strategies that we can develop for the way that we farm and the way that we live, the way that we get around. We have enough knowledge and we have enough technology right now to start making a huge dent. And it's really about a matter of will. And in order to build that will, Jen's last point is we can talk to each other. I really can't emphasize enough how important I think that is, right? There, we know from public polling, public opinion polling, that we have a consensus in this country. The vast majority of Americans understand what's going on and actually agree on a lot of policy solutions, a lot more than agreement than we certainly see in elected officials. And so talking to each other, reinforcing that, finding those points of agreement and pushing hard on elected officials, on corporate leaders, on decision makers at all levels to make the changes that we need to see.
Okay, thank you so much, Heather. And Jennifer?
Well, I see that our time is up, so I just want to reiterate the fact that there's whole populations of people that really contributed almost nothing to this crisis, but yet they're being affected by it the most. And so we really need to take into account the fact that we've created this situation for them, and we really need to help them get through this period while we address the underlying disease, which is, of course, this concentration of greenhouse gases, that bathtub that's filling too fast. So I just think we all need to think about all these people in the world who we're affecting, and they really have very little resilience to adapt to a lot of these changes.
Very well said, Jen. Thank you so much. So thanks to both of you for this very engaging and enlightening discussion. And I'm sure people are now equipped to look at the jet stream and its impacts with a good deal more insight and respect for how nature works.